Okay. So today we're going to see the third section of this course, which could be the optimization problem formulation. And at the end of this class, I will also give you some guidelines for the second homework that you will have to do. Actually, in the first class, when I introduced the course, I told you that in this class I will also give you the guidelines for the class project. But actually, I'm thinking I'm going to do that next week, at the beginning of next week class. So then the class project will be a group project. So it would be a good idea to start making some groups between you. So you decide who you want to make the project with. So you're 20 people. So I think in groups of maybe 2 or 3 people will be nice. So just please, over this week, send me an email saying what the groups you've decided on, and if somebody is left behind or anything, just greet me as well. It's a shame that we have group projects while doing the classes from home, because it's not the same as working together. I don't know if you're working together in person there, but I mean, if you do, it's the best for the project, I would say. Maybe not the best for the pandemic and everything, but I don't know. So please, during this week, I will put it in the webpage as well, and maybe I will send you an email later today, so people that couldn't come to this class also get it. So please start thinking about forming groups of 2, 3, even 4 people. It's okay, I think, for the class project. Okay. And as I said, I will give you the guidelines for the project next week. Okay, so let's start with this section. So this is what we're going to see today. We want to start with the optimization problem. How does it look like? Then a little section on the basics of optimization that I'm sure every one of you already know, but just to refresh your minds and to give a little bit of context. This is not something that I want to focus on, but yeah, it's nice that it's there. Then we're gonna start talking about how to state the optimization problem. We will give some examples and finally some recommendations in general. So let's start with the optimization problem. So what are the ingredients of an optimization problem as we are going to think of them? Well, first we have an input, which is then the objects that are given to us, the variables which we are working with. Then we have an output, which is the object that we are trying to find, the object that is sought. Then we have some constraints that are the requirements for that output. And finally, the objective function, which is a function that defines the cost or the objective that we want to optimize. And this over here is the main idea I want you to take from this class and in general from the course, because we are going to start working. The homework one and the class project could be focused on this idea, on defining what the inputs are, what the outputs are, and the constraints and the objective function, and apply it to an ATM problem. So let's see what this looks like. So an equivalent formulation for this problem would be, for an input, we will have given. So given some objects that are given to us, find something such that some requirements are met and that an objective function is minimized or maximized. These are equivalent. You can formulate the problem using these two formulations. We're going to focus more on this formulation on the left. But this over here is as valid as the other, and they are totally equivalent. So in this case, the inputs will be given, the output is something that we want to find, the constraints are something that are, I'm sorry, can you give me? I'm sorry, I'm sorry for that. I'm back. The things that comes with working from home. So I was saying, yes, these two formulations are totally equivalent. We have the input, that's something that is given. The output, this is something that we want to find. The constraints that are the requirement for the output, and what about variables and parameters? Okay, so this is a kind of nomenclature that we are using in this class, but variables or parameters are perfect as well to describe. It is in the inputs and constraints. Yeah, exactly. So in the parameters would be the input, and the constraints, that's something that's given to us. We don't have power over that over those parameters. That is something that is given, and the variables is something that we have control over. That's something that we want to find what's the best for us, which would be equivalent to the output. So in terms of variables and parameters, the parameters would be inputs and constraints, as Oliver said, and the variables would be the output of the problem. Okay, and of course the objective function would give us the relationship between the parameters and the variables. So this is an example of what an optimization problem would look like in this class. From your question, Eric, I assume that you already work with optimization problems in other class, and so I'm sure you have formulate these problems maybe in a different way, maybe in a more mathematical way. But we are going to try to formulate the problems in this class using this form over here. Okay, this is totally fine to formulate an optimization problem using any other formulation that you learn in other classes or that you're more comfortable with. But in this class, we're going to try to focus on this formulation over here. And I think this formulation is very nice for coming up with the formulation, the statement of the problem, while taking into account all the different points that should be considered, and also to give us a guideline to follow when trying to formulate an optimization problem. So we're going to try to focus on this, but as I said, any other formulation, as long as it's rigorous enough and clear enough, is okay as well. So this is an example that it's from an assignment that was done by students in this class some years ago. So the problem that they studied is the allocation of airport fixes during weather events. So in here we see the airport. This circle over here represents the terminal maneuvering area, and in these red spots are weather events when the aircraft do not have access to the airport. because of these weather cells. So they try to find the fixes around the boundary of the terminal maneuvering area in order to maximize the number of fixes that they can include. This is something that a student come up with, and they elaborate their project based on this idea. So in this idea, the input could be a circles that's called C, which represents the terminal airspace boundary. So this circle over here, the black one. Then we have green arcs over this circle. So these three over here, it represents the location where the fixes can be. Then we have a number D, which is the minimum angular distance between fixes. In this case, it's 90 degrees. So this would be the angular distance between two consecutive fixes. So this is the input, the data that they have. Then we have the output that could be a set of points on C, which is the location of those fixes, this over here. And the constraints that are that the fixes must be in these green arcs. They must not to be over these areas over here. And also the angular distance between the fixes must be greater than this distance D. So the objective function in this case would be the number of fixes. This is something that we want to maximize.
I have a question.
Sorry, you were saying?
What is an airport fixes?
Okay, a fix is a point on that represents a point in the trajectory of the aircraft that the aircraft has to pass through, maybe because a air traffic controller has told him to do. They are usually located at the borders of different areas. So for an aircraft fix could be a point where all the not all, but an aircraft can have several fixes, but it's an special point in the terminal maneuvering area that the aircraft have to pass through in order to do the descent approach or the arrival route. So this is a point that it's given by an altitude and some coordinates, and they represent a point in the trajectory for doing the route that the air traffic controllers want the aircraft to do. So it's more used in the context of standard maneuvers in around an airport, either departure or arrival. And if you try to look up the charts of an airport, for example, in the standard terminal arrival routes, the star. So if you want to give it a look, I will write to you in the chat. So the star, it's a standard procedure for arrival at an airport. So in these procedures over here, they are given a given number of points, which can be these kind of points which are fixes. Okay. I don't know if you can probably find this information for every airport that is controlled, maybe in any NSP webpage. So yeah, give it a look if you want to these kind of procedures. And yes, these are points that help the aircraft in the arrival routes or the departure routes. So yeah, the fixes are, I don't know how I did that. Yeah, the points that are important for arrivals and are important for departures. Okay, so this is an example of a problem, and this is what we want you to do. This is what we want you to do in this class for homework 1, from homework 2, and for the class project. This is what we are going to try to define today. What's a proper formulation? What do we have to consider? And yeah, so keep in mind, this is like the big thing for today and for the project and homework too. Okay, so in this equivalent wording that we talked about earlier, this could be the equivalent. So we have given a circle C, an arc on C, and a number D. Find a set of points on C, which are the location of the fixes, such that the fixes are located in the green arcs, and the angular distance between fixes is greater than D, and the number of fixes is maximized. So you can choose whatever you think you are more comfortable with. I personally like this one better because it's much it feels more natural, given, find, such that. But this over here is more schematic. It describes better what's inside those bins. So choose whatever you want. Either of those are perfectly fine. Exactly. Visual. So what I want you to do is to come up with a formulation, not to solve it. So you will come up with ways of solving it in another class or in another point of your life. So in here, we want to take an ATM problem and we are trying to give form to this optimization problem. So our task would be prior to solving that problem, okay? So the mathematical optimization problem will come after we have done this. And yeah, we're trying to do the, how to say, the planning part. So yeah, in this class we're not going to see algorithms, we're not going to see, I don't know, programs or anything, just an interpretation of ATM problems and what would they look like in an optimization formulation. And also this will give us the tools to interpret optimization problems that we read in papers and such. So being able to identify what's an input, what's an output, what are the constraints, etc., in a real ATM problem that's being studied in a paper or something like that, I think this kind of formulation is very useful for that. Okay, so let's talk a little bit about the basics of formulation. This is more related to the mathematical aspect of it. So this is something that we have to have in mind in general, because otherwise it would be very difficult to understand what other people are talking about when talking about optimization. So we have to have these concepts in mind, and I'm sure you have already worked with them, so it's nothing new. So let's go a little bit over this, but this is not the focus of this class, okay? But as I said, it's something that we have to have in mind, because if we are reading a paper about an optimization problem, this is the kind of things that they are going to talk about. We're not going to find this in a paper or in a communication. We're going to see more mathematical things. But when we're talking to the general public, or we're talking about, I don't know, a concept, this is what we're going to see. So the basic of optimization, an optimization problem is the problem of finding the best solution among a set of possible solutions. So an optimization problem would have three components. The first one would be the objective function. It is the quantity that we want to maximize or minimize. In the context of ATM, it can be the cost, the delay, the capacity, whatever thing you can imagine. Then the variables are the objects of the problem that the decision maker, that you have the control over. In the case that we saw before is, for example, the position of the fixes in the TMA. Another possible problem would be the number of air traffic controllers that there are in a sector, or whatever decision variable that you can think of. And then we have the constraints, that are the limitations on the values of the decision variables. In again, as taking an example, what we saw in the example before, a constraint can be the distance between the fixes, the capacity of the air traffic controller that has to be larger than the number of aircraft that they can handle, etc. Then we have a different classification of optimization problems. Again, this is not the subject of this class, but something that we can have in mind. We have continuous optimization and discrete optimization, depending on either whether the decision variables are continuous or are discrete. And we can have also a mixture of both, which are called mixed integer programming. And when they are discrete, it's usually called integer programming. Then we have constraint optimization versus unconstrained optimization, depending on whether the constraints exist or not. We have linear optimization versus nonlinear. Linear means that the objective function and the constraints are linear functions. It is usually called linear programming. And the nonlinear optimization, the objective function and the constraints are nonlinear, and this is usually called nonlinear programming. Then we have other classifications, for example, a single objective versus multi-objective, or deterministic versus stochastic, and another list of classification that you can find over there. But yeah, this is something that I just want you to know that it exists, and maybe you already know. But as I said, this is not something that we're going to focus on, so I'll continue. Another thing to have in mind when talking about optimization is that an objective function can have more than one minimum or one maximum. It can have a global minimum and maximum, which are the lower value of the minimum or the higher value of the maximum, and the local, which are all the maximums and minimums in between. And sometimes it is impossible to know whether a maximum or a minimum is global or not. So that's something that we have to have in mind when trying to solve an optimization problem. But again, because we are not trying to solve it, we are just formulating them, we will leave the solving part to those that are worried about it. And then we have some solution methods that can be the mathematical solution, derivating the function and setting the first derivative to 0, using brute force, using gradient descent methods or meta-heuristics, and another list of solution methods that's really big. So if you are interested in this, just give it a look on your part. I don't know if you have already worked with some of these optimization methods in other classes, in other courses. But as I said, we are not going to be using them. But when we are going to be reading papers, and we're going to be reading communications in conferences and such, we're going to find these solution methods. We're going to find this over here and this over here. So it's nice to have them in mind. But yeah, it's not something that we're going to focus on today. So I will pass. Okay, so now we're coming to the most important part, which is how to state the optimization problem. So how do we decide that the problem formulation is good? So the most important thing is that the formulation is understandable. It must be understandable for the people that are reading your paper, or the professor, the lecturer, whatever. Whatever your public is, it should be understandable to them. And also, what makes the formulation understandable is two things. First is rigor, and the second is clarity. And in here we have a quote from somebody named Terry Tao that says, The point of rigor is not to destroy our intuition. Instead, it should be used to destroy bad intuition while clarifying and elevating your intuition. And here's an article about rigor and clarity and how they are important and how to balance them. So in this class, we are going to try to balance these two concepts. So in rigor, we have things that are formal, that are dry. The problems are uniquely defined and they are very well defined, and every term is known and is defined. So this would be the equivalent of this mathematical formulation of a problem. Everything is completely academic, I would say. Everything is named, is defined, and it can be very formal. Whether clarity, we're working with informal language, with terms that are well known, and with colloquial language. So this is more like you are talking with a friend, or we're talking to somebody that is not an expert, and you're trying to explain to them what your problem is about. So how do you find the right level of rigor versus clarity? So there is no answer to this. In general, it depends a lot on when you're talking to. If you're talking to a specialist that has many similar problems, or that is actively working on the subject, you may have to use a more rigorous approach to your problem. So you may have to define everything very well, include equations in your formulation, etc. But if you're talking to the general public, or something that's not somebody that's not as experienced in the subject, you may use a more clear formulation, maybe not defining everything, not because the more things you define, the more things you give a mathematical context to, the more difficult it gets for somebody that has not all the experience on that subject to understand. So you have to find a balance between these two. And because we are in an academic environment, we are having a class on ATM and we're having a class on optimization, I want you to lean more towards this side of things, because we are not the general public anymore. We know we are working with papers, we're working with scientific approach. So the more you lean towards the rigorous side, for me, the better, while not completely giving into the mathematical formulation of everything. So this is an example of what I'm trying to talk about. This is an example that is not related to ATM, it's just pure math. It's an example which is the Goldbach conjecture that was stated in 1742. It's one problem that I think is not solved yet, but we have two different approaches to define this problem. So the first one over here would be the rigorous one, and it's this one over here for each integer, blah, 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 there are primes, blah, blah, blah. Okay, so this over here is perfectly okay, but you may have to have some knowledge in mathematics to follow it and understand it, and it's not completely direct to the reader what they're trying to talk about. Maybe something that some scientific that is very used to this kind of formulation, it will see it right away, as I hope you are. But for the general public, it's not as easy to see. And the clear and simple explanation would be every even number can be written as a sum of two prime numbers, which is very simple to understand, it's very clear, but it may lead to questions. for people that know more about the subject, or even for people that don't know that much, but they are trying to understand the problem better. So, for example, one question would be, every even number can be written. So, is there any condition on this even number? Well, from this formulation, we cannot see it, but in here we can say that this not even number have to be larger or equal than 2. So in this formulation, they answer a question that in here they don't. Or, for example, another question that you may ask, has the 2 prime numbers have to be different, or can they be equal? Well, in this formulation, they say that they can be equal. So in this formulation, they don't. So again, this is clear, this is simple, this is fast, but it may lead to questions. This over here, it's difficult to understand for a lot of people, but it doesn't leave behind anything that we need in the problem. And also it depends on your audience. If you're working with experts, let's lean towards this side, and if you're dealing with the general public, let's lean towards this side. So if we have a balance between experts and total beginners, I would say let's lean towards the experts, but not staying over the top. Okay. And also, I may say the clearer your statement is, even when working in an academic framework, the better. Because some people make things so difficult that it's impossible to read, and if you can make it clear while defining your problem very well, that could be the ideal. Okay. So the solution, it's rigor on demand. This means that you have to be as rigorous as those that are reading you or are listening to you demand. So if you're talking with an expert, you will have to give more rigor, and if your audience does not require that level of demand, then just you don't need to be that rigorous. So you have to do this, you have to be ready to refine and define. So first, you start with stating your problem very clearly, maybe without specifying all the terms. This will be like a version 2.0.1 or something like that. Something very simple that can lead to a lot of questions, but something that you are comfortable with. And then, if necessary, you start to define things and to refine. So you start adding more rigor as you go. So when should we refine and define? So first, you should know the definition of all your terms in advance, even if you don't use them all in your first version. But all the terms that you use, you should know the definitions of. So for example, in the problem that we had before, of the TMAs and the fixes and everything, you have to know what is a TMA, what is a fix, what is the weather that you're working with, what kind of objects they are in your problem. So all of this you have to know because you're stating your problem. So even if you don't define them in your statement, you should know in case somebody asks, or in case you see that your approach is not rigorous enough, so you can add them later. So don't wait for people to ask questions, so anticipate for the demand for rigor. As I say, it depends a lot on your audience. So if you're writing on a scientific paper or you're writing your thesis, have in mind that the people that are going to be reviewing your paper or that are going to be reviewing your thesis are experts on the subject. So anticipate that these people are going to need a high level of rigor. But if you're I don't know, doing any kind of or the kind of projects where you know the people that you're going to be working with do not need this level of rigor. For example, we're talking with your colleagues about what you're going to do for the class project. You don't need to define everything in advance, or sorry, you don't need to define everything in your version, or define or refine to a higher level. And again, be prepared to be rigorous down to any depths. So this comes in relation to this one. You should know your definition of your terms, and you should be prepared to add more levels of rigor if you are being asked, or if you feel that something that's beneficial for you. So for the definition part, these are the three things that you're going to need when defining something. First, you have to know what kind of object it is. For example, we define X, and it can be a number, it can be a matrix, it can be a sequence. What kind of object it is? So for example, in here we have an example of a staffing plan. So in here they say that the staffing plan is a sequence of shifts. So the kind of object is a sequence. Then you can add some name or notation. It's not always necessary, but you must use it if it's helpful. For example, in here, the notation for the sequence, the shifts is S1 to Sn. So the shifts have a nomenclature, which is S, but the staffing plan has not been given a name. I mean, a staffing plan, but not like a mathematical variable or anything. So just use those notations if they are helpful. So, and also you have to define, you have to give the properties for that object. In this case, with the staffing plan, we have a sequence of shifts. Okay, this is the definition, and then the properties. The properties are such that shift S sub I plus 1 starts before shift S sub I ends for all I. So this over here, the such that etc. would be the properties. The sequence part would be the object, and the notation would be the mathematical names that you're given to these values. And yeah, this is the definition of a staffing plan. But in this definition, you still have some questions that the reader may have left. So one possible question could be, what is a shift? So that's something that you have to anticipate, and you have to clearly know what a shift is in order to define it if you think it is necessary. So let's go back to the example. So let's see how we are going to state the problem. So for example, we're starting with this one. So in this first approach, the statement would be to put fixes in airport airspace during a weather event. Well, of course, this is not rigorous enough because we don't have, we practically, we have so many questions left, like why, are you going to put those fixes? What is the airport space? How do you define the airspace? How the weather event affects the airspace? So there's a lot of questions that are not being answered. It demands more rigor. So we're trying to reformulate this, adding a little bit more rigor. So another statement now it would be to allocate the maximum number of fixes onto the boundary of a weather-impacted terminal airspace. This has a little bit more explanations. For example, the put fixes now is allocate the maximum number of fixes. So now we're seeing how do we want to allocate those fixes. And we also have a definition of the airspace, which is the boundary of a weather impacted terminal airspace, but we don't have the information about how the weather impact this airspace, whether there is a limitation on the number of fixes, because I mean, for this statement only, you can have infinite number of fixes. There's nothing that prevents you to do it. So we need more rigor, we need more definitions, and try to answer up these questions. This over here is not rigorous enough. There is a lot of questions unanswered. And this over here could be a mathematical expression of the problem, but maybe it's too formal. If we say that we have this input, a circle, arcs, and a number, we have an output, which is a set of points, and we have a constraints, which are the points must be on the ring arcs, and the distance between the points must be a given distance, and the objective function is a number of points. Okay, this is closed in the mathematical sense, but what is it? I mean, this means nothing to me apart from a mathematical problem that you come up with. So this has no relationship to ATM, no relationship to a real problem at all. So this is not clear in any level. This should be, if you want to include this, which is perfectly fine, you have to include an introduction to your problem, you have to include a clear definition of what these terms relate to ATM, to your ATM problem. So if you have a paragraph before this explaining what the circle is and the arcs are, this distance is, this is fine. But what we're trying to do is to try to find a balance between formality, between rigor and clarity. So in a single view, we can see all the elements that we need, both related to ATM and in a rigorous way, mathematically speaking. So this could be the right amount of rigor. This is what we're looking for when you are solving, well, not solving, when you are stating your optimization problems. We have the variables, the objects, they are defined. This is a circle, this is an arc on a circle, this is a number, these are defined. They are also given names, C, D. They have the properties that they define them. For example, the properties of these ring arcs would be that they are on the circle, or I don't know, whatever is necessary to completely define it. And also we have what they represent. How are they related to the actual ATM problem? So the circle C represents the terminal airspace, the arcs represent the popsicle fixed location, etc., etc. So we have come from this, which is just a sentence that is not an optimization problem at all, to this that is too formal and means nothing related to ATM, to this which is a mixture. It takes the best of both worlds, which has rigor on the one hand and clarity on the other. So this is what we are trying to aim for in this class, and this is what I want you to aim for when you're doing your homework too and your class project. You're going to find a problem that you are going to write your optimization problem about, and you're going to try to put your problem like this. So the conclusions for the rigor versus clarity debate could be that there is no definite answer in the level of rigor that you have to use. It's so subjective. You decide what the level of rigor is, or maybe your teacher will decide what the level of rigor is when you give in your assignments or whatever, or the reviewer for the journal. So it would be dependent on the audience. So we have the specialists versus the general public. And you should be prepared to provide any level of detail and to provide rigor on demand. And we're trying to see now how to work out the statement. So maybe this would be a good time to make a little break. It's 2 already. So maybe we can, let me see what we have left. Yes, like half. Okay, perfect. So let's take a little break here, if you don't mind. So we can have like 10 minutes or so. Are you okay with that?
Yes.
Okay, perfect. So if you don't have questions about what we've done so far, I will see you in 10 minutes.
Can I ask you one thing?
Yes, sure.
When did you say that that we should email you about the groups for the class project? When was
during
last day?
this week, or during the week? I will send you. I will send an email to the class.
Will we do homework 2 in groups also, or
No,
is homework 2 individual?
Yes, it's individual.
Okay.
What's in project is the project is going to be done in groups.
Okay.
Okay. Well, see you in 10 minutes. Hey, we're back. Okay, let's continue then. I hope you're everyone there. So what have we seen so far? We were discussing what the rigorous and clear problem look like and what's the balance between the two. So now, using these definitions, using these concepts that we have seen, we're going to try to work out a statement. We're going to try to come from one idea of an optimization problem to a full statement of the problem. So the example will be to find the optimal time to close an airspace. So we are working with a problem where we have an airspace and it's necessary that it's closed for a certain amount of time. And we are trying to decide what's the optimal time for this airspace to be closed. So we're going to decide when we're going to close this airspace in order to maximize some benefits or minimize some cost. And we're going to try to define and state our optimization problem. So we have this problem over here, and we're going to start with a simple statement, which is close the airspace optimally. Of course, this statement over here needs more rigor, because what is optimally in this problem? We don't know. So to add more rigor, we are going to try to define what optimally means. So in the case of the airspace, we are going to close the airspace as to minimize delay. So in this statement over here, we can see that the objective function is starting to show up. We have the delay as our goal as our variable to minimize. So of course it demands more rigor, because what is delay in this case? We have to keep defining. So in our third approach, we're going to try to define the delay. So we are going to try to explain our problem. So we say we want to close the airspace as to minimize delay, whether delay is the total delay. Well, what is total of what? We have to keep defining things. We need more rigor in this case. Then we define even further. We want to close the airspace as to minimize the sum of delays for all aircraft. Okay, in here we have another term that was not there before, which is aircraft, and we see that we have a lot of them. And the delay, the thing that we want to minimize, which is the total delay, is defined as the sum of delays for all aircraft. Okay, so we are getting there. We are having more answers, but still it needs more rigor. For example, how do you define the delay of an aircraft? Well, we are going to try to do that. So we are going to define delay even further. So we want to close the airspace as to minimize the sum of delay for an aircraft. And now we define delay for an aircraft, where the delay for an aircraft is the length of the closure if the aircraft is effective, or is zero otherwise. So the delay for an aircraft is if it's affected by the closure, it will be delayed time that's given by the length of the closure, or zero if it's not affected. Okay, so in here we can see that the objective function is taking a form that's very close to being completed. So we can define an objective function as the sum of delays for an aircraft, where the delay of an aircraft is zero if it's not affected, and the length of the closure if it's affected by the closure of the airspace. But in this definition over here, we can think, well, some question that comes to mind is, well, what is the length of the closure? Is that a parameter that you have? Is something that you have to define? Well, in this case, the length of the length of the closure could be something that's given in our input. So we have, in our problem, we have to close the airspace for a given amount of time, and that given amount of time is something that is fixed. So that will go into our input. And also we have to know what does it mean that the aircraft is affected. That's something that we have to define even further. So even if we have arrived to this objective function, there's still more to do. So we have to be able to compute this delay. So for that, we need, as I said, the length of the closure. So we're going to name it because it's beneficial for us. So we are going to name it L, with the letter L. And we have our first input object, which is L, which is a number that represents the length of the closure. We don't have to name it. You don't have to put this L over here. But if you find that it's beneficial for you to name it because the problem is more clear, or because you're going to use it, I don't know, for the objective function of whatever, then you name it. In this case, we have come up with a name for it, L, and we put it in our input. So we can reformulate the objective function saying that the delay of an aircraft is L if the aircraft is affected, or 0 otherwise. And the total delay is the sum of delays for all aircraft, which is equal to this number L times the number of affected aircraft. So because L is a parameter, is an input, and it's something that it's known to us, to minimize the total delay is the same as to minimize the number of affected aircraft. So we can say that an equivalent objective function that it's easier for us to write in the statement is that, and now we want to minimize the number of affected aircraft. So the objective function would be the number of affected aircraft. We can say we can still say delay, but because we have already because we have defined delay is in this simple way, we can put the objective function in even a simpler, in even a more simple way. So we have formulated this. So we are going to try to organize this into the pins that we state at the beginning of the class. So the first input that we have is a number L that is indicating the closure, the length of the closure of the airspace. The output would be the time indicating where the closure starts. This we have named it with a letter T. We don't need to do that, but in this case, we have done it in order to, I don't know, to make things a little bit more clear. So T is indicating the closure start time, and this is the thing that we will have. This is what the equivalent in the mathematical form would be our variable, where variable will be T, and L would be our parameter. The constraints so far, they are known because we have there's some things that we have to consider yet, and the objective function is the number of affected aircraft. So we are getting there. But some questions may arise. For example, how do L and T affect the problem? So far, we haven't said anything about what means that the airspace is closed for a time interval L, and what does it mean for this time interval to start at T. So we have to define what an affected aircraft is, and how is the aircraft affected by the values of L and T. Also, it would be nice to mention the aircraft before the objective function, because we have it here, number of affected aircraft, but in the input there's nothing about them. So where does this come from? Well, it would be nice if we include it in our inputs as well, because we have to know something about this aircraft, right? So our task is to fill the gaps in general. First, we want to define what is an affected aircraft. So first, how many aircraft can be affected? When we can define a set of aircraft from 1 to n. And this is something that we must include on our input. This is something that we are going to be giving at the beginning. So you have a set of aircraft that are going to try to enter this airspace. So how are the aircraft affected by L&D? We need a model for this, for how the aircraft are affected. So we have for each aircraft and the airspace entry time, which is S sub I, and the airspace exit time, which is T sub I. So we have these two are numbers are given for each of the aircraft, that we have 9 of them. So these over here are our inputs as well. So we have this number of aircraft that want to enter the airspace at a given time and to exit it at another given time. So the aircraft will be affected by the closure if the interval t to t plus l intersects the interval s sub I to t sub I. So in this example over here, in this illustration, the aircraft in particular will be affected by the closure because this interval over here overlaps with this one over here. If the aircraft were to enter the airspace earlier and to exit the airspace before the closure of the airspace, it would not be delayed and it would not be affected. So this all the number of aircraft, the airspace entry times, and the airspace exit times for all the aircraft must be included in our inputs. And also this definition over here, of course, is going to be included in the objective function. So we have something like this. We have the input that we had before, which is a number L that's indicating the closure length. And also we have new inputs. We have a set of aircraft that go from 1 to n. And for each aircraft, we have two numbers, which are the airspace entry time and the airspace exit time. Also, we have 2 times n new inputs. The output is still the closure start time, which have the t. The constraints so far we have known, and the objective function is now the number of affected aircraft, but we have included the definition for an affected aircraft. So aircraft I is affected by the closure if the time interval t plus l intersects these values over here. So I can see that naming L and naming T has been useful to define the objective function. So in this case, it was beneficial for us to name this. But if you don't need it, you don't have to. So finally, there are more, we're almost there. There are more, another question that may arise, which is, for example, okay, well, I will close it. If I want the aircraft not to be affected, then I will just close it never. I will close it at t plus infinity, and that's not something that that's possible. So that's actually what makes this problem trivial. If you have an answer that it's completely completely trivial in the sense that it doesn't require any computations at all, any solutions, you don't want that. So in order to avoid triviality, we have to do something extra. So in this case, what we're going to do is to add constraints that affect t. So we are going to say that the time of the closure must be over a lower limit and under an upper limit, because otherwise we will just close the airspace 100 years ago, and that's not something that makes sense in this problem. But that's something that we have to include in here, because otherwise the problem is open to those kind of interpretations. So we want to include these constraints to prevent this from happening. So finally, this is a statement that we come up with. We have two new inputs, which are L and U, that represents the closure start, lower and upper limits. And we have a new constraint, which is defined by these two inputs. And this is an example of what the problem looks like. We have a given number of aircraft. In this case, we have represented just one of them that enters the airspace at a given time and exits it at another given time. We have the limits for the airspace closure, and we have a closure that has a length L. So finding this number T would be our goal, and we want to find it as to minimize the number of aircraft that are affected. So this is what our statement would look like after answering all these questions, after being more rigorous step after step. Are there more questions that may arise? Well, I guess so. For example, I don't know, let's say, are these numbers I don't know, is T given, is T continuous, for example, or does it have to be given in intervals of maybe 5 minutes every 5 minutes or so, or we can give a continuous number for T? That could be a question that may arise. For example, is it okay to say that we have to close the airspace at minute 5 with 32 seconds and 1 millisecond or something like that? Maybe we have to give an integer for that time. So maybe in intervals of 1 minute or in intervals of 5 minutes, whatever restriction we may add. So these are things that we can include little by little, anticipating the questions that the audience may have. But this is a statement that's close enough. So this is pretty close. And of course, if we are working with a given problem, we will have to include all the questions that may arise from analyzing that problem. Okay, but this is something that's closed and that we can call our first version. So again, with the rigorous versus clear debate, if we say this over here, we want to close the airspace optimally. This is not rigorous at all. There are too many unanswered questions about all that we saw. And if we say this, given blah, blah, blah numbers that are this over here, find T, where T is between these two numbers, that minimizes the sum of blah, blah, blah. If we say this, we are stating the mathematical program of the problem, but this makes no sense if you don't provide any further explanation. This has nothing to do with ATM. We don't know what this is about. It's just a problem that means nothing. So we have to give some relations to ATM and to give something like this, that is something understandable and is something rigorous. So again, not rigorous, too many unanswered questions, and not clear. We need clarity in this statement over here. Also, an important thing is to have a nice structure. So for example, in here, we have a set of aircraft, and for each aircraft, we have a given number. So please structure your objects in a sense that they make sense. For example, in here, our inputs can be, we have set all in the same level. So a set of aircraft, that's 1n. And for another set of 2n numbers, which are S1 and S2 and T, sorry, SI and TI, representing blah, blah, blah. So in here, it is clear that these two are related. So why not put it in a clear structure? So, okay, this is, the problem could still be okay, but this is more clear than this statement over here. Okay, it's easier to understand. It gives us an additional information, which is that these are the same kind of objects, as to say. And that's something that I want you to include in your homeworks and in your projects. So please state the relation between objects in the input and output. Okay, so something that I want to make clear is what's the difference between our problem statement and the mathematical formulation. So our task is to find this problem, given blah, 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 find the output such that it meets the constraint, and it minimizes or maximizing an objective function. This is written in plain, clear language, and including some symbols are okay, as we saw earlier. These are symbols, of course, and it's okay to include them. But what I don't want you to do is this over here. So in comparison, we have the standard mathematical formulation of a optimization problem. This is something that you may have seen in other classes, or that you have to work with I don't know, I'm not sure if you have some, I don't know, algorithms class or something like that, but you may have seen this formulation. It is minimize a function that has as an argument x, subject to equality constraints and subject to inequality constraints. This formulation is very useful, but not for us, because this is very useful where we are trying to solve the problem. So once we have done this, then we may start to think to formulate it like this. But because we don't want to solve the problems, this formulation over here is not entirely useful to us. It's very useful, again, if we want to solve the problem, but that's not our case. So this formulation over here is too formal for this class. And also, if we just say this, if we just put the equations on the plate, it has no value for us. I mean, it has to have some relationship to ATM. So what I want you to have in mind is that please don't use this formulation for this class. It is okay to use it in addition to this problem. So this is our task. Of course, if you include this formulation on the class project as, okay, this is our problem, if we want to solve it, we would have to write it like this. It is perfectly fine to add it again as an addition, but the problem statement, which is this one over here, is what it's our task. Okay, so now we're going to see some examples. For one example that comes from the same year is one of your colleagues solved this problem. State this problem, which is the problem of assigning air traffic controllers to sectors. So they have a number of air traffic controllers that are needed in a sector, and this number is a random variable, so it's not a given number per se, but yeah, a random variable. And they have the probability distributions of these needed air traffic controllers that depend on the situation of the sector, whether they have weather or they have more complexity in the traffic, whatever may affect the sector. So we are given the probability distribution for each sector, and this gives us the probability that at most a given number of air traffic controllers are needed, and we can compute the probabilities of having an understaffed sector. So this is something that this is the information that they had, and this is the problem that they came up with. So as an input, they have a number n that represents how many air traffic controllers are available. They have a set S of k sectors, and for each sector S under lowercase in S uppercase, they have a distribution which is called F sub S of the number of required air traffic controllers. So again, number of available traffic controllers and a given set of sectors, and for each sector a distribution. The output that they are looking for is for are k numbers, n1 to nk, that represent how many air traffic controllers are assigned to each sector. So we have a number of k sectors. For each one of the sectors, they would need a number representing the number of air traffic controllers that are going to be assigned up to that sector. So this is their outputs. The constraints are, of course, that the total number is less than the sum of the total available air traffic controllers. And the objective function is to minimize, well, the objective function is the probability of having an understaffed sector. And the objective of the problem would be to minimize this probability of having an understaffed sector. So they, from this information that they found in the papers or they come up with, they state this problem over here. So let's give it a look to other examples. For example, this is path planning in some sectors. So if the input in this case, we have a region of interest, which is this one over here, which is a simple polygon that's representing, for example, an area control center. We have a set S of sectors that each one is represented by a polygon. That's a partition of that region of interest that this one's represented over here. And for each sector, we have a weight of that sector. We have 2 points, S and T, in the region of interest, S and T, that represents the origin and the destination of the path. And the output would be a path that goes from S to T, the path that we have named P, and this is this one over here. The constraints are that the path must remain within the region of interest, and the objective function is the total weight of sectors intersected by the path. So the objective of the problem is to minimize total weight of sectors intersected by the path. So in the end, we're going to try to find the path that minimizes the total weight of the sectors that they pass through. These values can represent, I don't know, the taxes that the airline has to pay to a given country, or maybe the delay that they are experiencing during while passing through these sectors, or whatever is related to your ATM problem that you're trying to solve. And for last, we have another example, which is sector joining. This could be useful, for example, if we want to have one air traffic controller to take care of a multiple number of sectors or something like that. So we have as an input a region of interest. That's again a polygon representing the area control center. We have a set of sectors that partition the region of interest, and again we have a weight. The output must be a subset S prima of sectors. The constraints is that the subset must be convex, and the objective function is that total weight of sectors is the total weight of sector is in S prima. So we want the objective of this problem would be to minimize this total weight. well, comparing these three problems, all three of them has sectors in the input, but they are treated differently. For example, in this one over here, the sector is an element, and the geometry is not important at all. We just need the number of sectors, and that's it, and the probabilities in each sector, and the connectivity is also not important. In the path planning problem, the sector is not an element anymore. It is given by a polygon. The geometry is not important, but the connectivity between the sector is important. And finally, in the sector joining, the sector is again a polygon, and both the geometry and the connectivity is important. So we can see that even when they are having the same input, as so to speak, the sectors, in reality, they are not exactly the same input. In here, we don't need the geometry, we don't need the connectivity. In here, we need the connectivity between the sectors, and in here we need the geometry and the connectivity. So this gives us this arrives in the definition of our inputs. So we have to answer this question over here. We have to answer what kind of objects are given. It is not sufficient to answer what is given or what objects are given. We have to define the objects. For example, in these three cases, sectors are given is not enough. We have to define further. Okay? And finally, some recommendations and guidelines in general for the statement of the optimization problem. I want you to know the difference between objective and objective function. So an objective function is a function that has an argument. The arguments are feasible solutions, and it has a value. This means a number that we want to either minimize or maximize. It represents the cost or the benefit for a problem. We must state the objective function after the input, output, and constraints. Okay? And this is different from the objective of the problem. The objective of the problem can be to minimize the cost or maximize the benefit. So this objective function over here represents the cost and the benefit, but not the minimize and maximize parts, okay? So we, as a recommendation, try to state the objective at the end of the problem statement. So don't start with the objective is to minimize, blah, blah, blah. And this over here, it is wrong. The objective function is to minimize, blah, blah, blah. This is not correct. The objective function is this cost or this benefit, and the objective of the problem is to minimize or maximize, okay? That's something to have in mind. I'm sure you already do, but yeah, just the difference. And as we saw earlier, for example, in this over here, the objective function is total wave, probability. There's no maximize or minimize in here whatsoever. So this, how about this confusion is, before you state your problem, you may have an introduction. So in this introduction, you say what you want to do with the problem. You state the motivations. And in here, it's okay to say, we want to maximize the benefits, blah, 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 or we want to minimize delays. In here, it's okay to say that. In the problem statement, if you use this formula over here, don't say minimum, don't say maximum, and you will be fine. If you use this other format, which was explained at the beginning of the class, where instead of input we have given, instead of output we have find. If you say given something, find something else, subject to constraints, and the objective is to minimize and maximize, this is okay to say this. But if you use this problem over here, don't mention minimize or maximize. and after you state the problem, you can say some final remarks. So if you want to, you can say the objective is to minimize the cost or whatever. But if you use this formulation over here, don't mention minimums and maximums. That's just a recommendation to avoid the confusion between these two. And that's something that, I mean, of course we have it in mind, but I mean, I get confused sometimes as well. So just something to differentiate. Okay. What else? Okay. What is the difference between a calculation problem and an optimization problem? Because you will have to formulate your own optimization problem both from homework 2 and the class project. I don't want you to. Oh, sorry. To end up with something too simple. So the difference between a calculation problem and an optimization problem is that in the calculation problem there is nothing to optimize. You just have to compute something. So in this simple example of apples or oranges, that's something that middle schoolers could do, or either younger. We have given 2 apples, 3 oranges, the cost for the fruits, and we want to find the total cost, and the output is a number. So there is no optimization in there whatsoever. There's no, they just have this problem, just do it. Okay, this is not what we are trying to do. What we're trying to do is to define an optimization problem. So with this simple example that we are not going to use, of course, we have given this. So one possible optimization problem could be to find the 3 fruits that maximize the cost. And the output could be the 3 fruits that maximize the cost. The cost is not the output of the problem, okay? And this is, don't fall in these kind of problems. I'm sure you will be able to differentiate an optimization problem from a problem that is not optimization, but just in case. And also another guideline, we have to know the difference between the output and the value of the objective function. So for example, in here, we have an example that it's a graph with vertices, and there are 2 vertices that are S and T, and we want to find the path S to T. So our output would be the path, okay? And the objective function is the path length. So we want, the objective of a problem is to minimize the path length, okay? So the objective function is the path length, okay? But the output of the problem is the path itself. So the total length, it may be interesting to include it, but it's not the focus of the problem. Whatever the length is, we are not interested in that value. We are just interested on the path that minimizes that value, okay? Of course, if you give the value for this length, I mean, it's an addition, it can be interesting, you can draw some conclusions from it, but it's not your real objective. And also, sometimes there are some functions, some objective functions that are not interested at all, are not interesting at all on what their value is in terms of ATM. So sometimes I don't know if I can give you, I don't know, maybe, yeah, maybe this one over here, the total weight. You don't need the total weight. Who needs the total weight? You just need the paths. Because maybe these values over here means nothing to the pilot or means nothing to the airline, but you want to give them information about the path. So sometimes the objective function value at the end is not even interesting, okay? But of course, include it if you think it's necessary or interesting, but what we're looking for is the output of the problem. And lastly, some things to avoid. First, avoid too simple problems. For example, in this one, we have a number n, that's the number of planes in a sector, number k representing the air traffic controller's capacity, and we want to find the number of needed air traffic controllers. So the solution in here is just divide the number by the capacity, and you have the number of traffic controllers. This would fall in the category of these problems over here, okay? So avoid these kind of problems that are too simple and they have nothing to optimize. And the second recommendation would be to avoid redundant constraints. And you should keep only the constraints that are more restricting. For example, in the example that we had before, imagine that we had this other restriction over here, that is that t must be larger or equal than a given lower value of L sub 0. So imagine that we have this constraint. Well, if L sub 0 is lower than L, then this restriction, this constraint does not restrict anything. The problem doesn't change, so it doesn't make sense to include it. However, if L sub 0 would be to the right of L, if L sub 0 is larger than L, then it does restrict the problem, and then you must include it, okay? So yes, avoid redundant constraints, and that's it. That's it for the problem formulation. So do you have any questions regarding what we saw today? Okay. Okay, that's perfect. So yeah, this is what we want you to do for the class project and the homework too. And now I'm going to give you some guidelines for homework too. If there's no questions, so
can I just ask? We will not solve optimization problems in this class, right?
Exactly. No, we won't.
Okay. Okay.
That's something that maybe you will do in other classes or something, but no. Of course, if you want to go farther in your assignments, you may say, okay, this is how I would solve it, or this is how they solved it in the paper, or something like that. It is not required for this class, but of course, if you want, if you know how you would solve this problem, just please explain it. And I mean, it's not necessary, but of course it shows that you have fully understood the problem. But no, the objective of this class is just to formulate the problem. And it's not, I wouldn't say it's an easy task. Of course, solving it is more technical, but being able to look at an ATM problem and to draw conclusions from it and to be able to state the problems as we have done is very significant, because you have to think of all the possible questions. And again, if you're going to work with solving a real problem, you will have to do this as a first step. So this is your first step. State your problem. You will solve it later, but in order to solve it, first you need to define this completely. Okay. Perfect. So sorry, I can see. So now for our homework 2 guidelines. Okay. So this is the second homework. And what I want you to do is to look at published articles in the Design Innovation Days, the ICRAT and the ATM seminar, preferably from the most recent editions. But if you don't find anything that you find interesting in the newer ones, you can go with older ones if you want. These are the links for these 3 conferences. In here you will find all the papers and all the presentations, okay? Then just look at articles, and you have to find one that considers an optimization problem. So after you find this paper that has an optimization problem in them, not all of them do, but a lot of them have optimization problems, you must restate the optimization problem that was considered in the article using the format from this class. This is input, output, constraint, objective function, or the other formulation that was given, find such that, and minimizes, blah, blah, blah. You have to look at the papers, give it a look, find something that you're interested in, find an article that has an optimization problem, and take that optimization problem and formulate it as is it done in this class. And also the last step would be to give one sample instance to the problem. And we are going to see in a second what this means. So some notes in your homework, you must indicate, of course, which article you're using. Not that articles that are in this conference consider optimization problem, but you have to find an article that does. You can simplify, this is very important, you can simplify the problem that is stated in the article. So you can use the main idea of the article to state your own problem. Of course, if you simplify it, you must mention how you simplify it. Okay, this is going to be very useful because normally these problems are very complex, but you can also work with a simplified version of those. The problem statement is a short descriptions. As we saw today, they are very short. If it occupies more than one page, it's too complicated. Okay, so just if you see that the problem statement is longer than one page, it's too complicated, please simplify it or find another one. Also, you can use articles that are not from the conference that I mentioned. For example, if you found one in your homework that had an optimization problem that you like, you can use that. But in this case, please ask and send me the paper that you want to base it on, and I will say if it's okay or not. And then for the sample instance, so a sample instance consists on a set of values for all the items in your input and output. Okay, so just give numbers to what you define. It's a very simple example. It does not have to be realistic. If you can, please give a feasible solution. No, it doesn't need to be the optimal solution. Of course, if it's a very difficult problem to solve, or even if the feasible solution is difficult to find because the constraints are difficult functions, for example, describe what a feasible solution would look like, and check the consistency with your definition of inputs, outputs, and constraints. Okay, so let's see an example of what a sample instance is. So we have this problem. That's the one that we came up with the closure of the airspace. So this is the problem that we have a state. As you see, it's quite short. And a sample instance would look like this. So for example, the length of the closure is 30 minutes, for example. I totally made this up. The number of aircraft that are entering the airspace are 5, and they have these numbers for the entry times and exit times, and the lower boundaries and open boundaries have 5 minutes and 90 minutes. I'm just giving values to these numbers over here. And a feasible solution, for example, is 62 minutes. That's something that I came up with. Is it possible? We have to check with the constraints. Is T above L and under U? Well, yes, it is. And additionally, we can give the value of the objective function. So this would be the output. So the value of the objective function is the number of aircraft. We can give this additionally. And for example, in this case, the number of affected aircraft is 2. Okay, so just give some values and come up with a feasible solution, just to see that you understood what you wrote here, that these are not just symbols and definitions, that you can actually put values to those symbols. Okay, it doesn't have to be realistic. There would be papers when you can find these values exactly what the authors used, so that could be nice. If you don't, that's fine. Again, the feasible solution can be easy to find or not. If it's not, just say why it could be difficult to find, and explain a little bit what it would look like. And that's basically it. Again, please send it in PDF to my email. The assignment is individual. The deadline is the class in week 9, which is the first week of March. And the grade is the same as the other ones, U3, 4, and 5. Any questions?
So we can, in the sample instances, can we use whatever numbers we want, or are there any requirements?
As long as they are consistent with what you wrote in here, you can write whatever. Of course, if they make sense, it's better. Yeah, but it doesn't have to be realistic. But yeah, make it so it could be a problem. Okay, just imagine that I put here 5 years. It's not okay to close an airspace for 5 years. So it could be correct, but it would not make sense. Okay, it's not, even though if it's not it's not realistic, but you know, have a little common sense. Okay. Okay, any other questions? Okay, perfect. So I will send you an email asking for the groups for the project, and I will upload these guidelines and the slides to the webpage. Okay, I will see you next week then. Bye-bye.
Bye.